We're continuing with section 13.3, and we want to discuss the Arclength function. And then first we introduce the Arclength function, then we kind of explain why we need an Arclength function, and then we discuss the Arclength parameterization in this video. The length of the portion of the curve R of t over the interval a and t is, see, this is the arc length between a and t. So what you do is you go integral from a to t of the basically the derivative of the position vector, the magnitude of that, dt. Tau, sorry. Tau is a dummy variable, so you won't mix it up with t over here, and so instead we use tau for the inside, and this gives you the Arclength function, see, because t is the variable and you get s of t. The other thing to notice about s of t is that you're integrating over tau, and in magnitude is a scalar function, and you're integrating over tau. It's just integral of a scalar function is going to be in a scalar function, and so this s of t is a scalar function, and if you whatever t value you plug in, you get the length of arc length between a and that t value. So the next thing to notice is that we're saying that s of t is the arc length. And if we're discussing arc length and we're discussing moving particle, how do I find the speed of the moving particle? The speed of the moving particle at any time is going to be the derivative of s of t with respect to time. So I will have the speed is ds dt. And on the other hand, the speed is the magnitude of the velocity. So the speed should be the magnitude of the velocity. And the velocity, we can use the position vector to find the velocity. So velocity is r prime of t, and the magnitude of that is the speed. So speed is both this and that. Can we verify that from this formula? And that's the other question, because there are two definitions of the speed that I have. Are they matching using that formula? So let's take the derivative of this side and see what we end up with. So if I take the derivative of that side, what am I ending up with the fundamental theorem of the calculus is going to be the integrand evaluated at t, which is going to be r prime of t, basically. And so the two of them match. So the definition magnitude of the velocity and instantaneous change in the total distance traveled is going to be the same thing, and they're both the speed. And so the speed is going to be that. The speed is going to be that derivative. So we discussed that the speed at any time t is going to be equal to the derivative of the Arclength function with respect to time, and that is equal to the magnitude of the derivative of r at time t. And then we have another notation, s with a dot on top. That's a notation that is used for basically the vector calculus, and a lot of times in your physics you will see that instead of ds dt. That is, s with a dot on top means derivative of s with respect to time. Now, what is interesting about this arc length value? So arc length is an intrinsic property of C. That means that if you start from one point in the space curve and you end up in another point in the space curve, the length that you traveled on the space curve is going to be the same. You can have different speed traveling, and so at different time you can be in different places, but the distance that you travel, the total distance that you travel, is going to stay the same. Now, here's what we're saying. So let's say R of t is one parameterization of a space curve, and the parameterization takes from one initial point to end point is with t between a and b, and then let's say q of u is another parameterization of the space curve, and un is going between c and d, and then the arc length calculated with the first parameterization, which is going to be the integral from a to b of the magnitude of the derivative dt, is going to be the same thing as the arc length evaluated with the second parameterization. And again, the parameterization could go, one goes from a to b, one goes from c to d, but c and d give you the same pair that a and b give you in the parameterization with r, and c and d gives you the same pair in parameterization with q. And so let's do an example. Let's talk about the circle. We parameterize circle with all sort of things. One of the most comfortable is with sine and cosine. Let's say we're parameterizing as unit circle, and this time around we're parameterizing it with cosine of mt and sine of mt. So one full rotation for me is going to be 2 pi divided by m. So t has to be between 0 and 2 pi divided by m for a full rotation, and where m is not 0, obviously. And now let's use this parameterization and calculate the arc length. So first step is the parameterization, which we did. Then you find r prime of t, which is going to be derivative of cosine mt with respect to t is m negative m sine of mt. Then derivative of sine of t is mt is m cosine of mt, and then this is a parameterization in the xy plane. And so now I have to go this part to power 2 and that part to power 2, which is going to give me the magnitude is the square root of m squared sine squared mt plus m squared cosine squared mt, and this is going to be end up to be m. And so basically when I'm taking the antiderivative, antiderivative from 0 to 6 pi over m of m dt, and this is going to end up with 6 pi over m times m, sorry, not 6 pi, 2 pi, 2 pi over m, and that would be 2 pi, which you're expecting because the circumference of a unit circle is 2 pi, and that's another parameterization of the unit circle gave me the same value. Now let's see why we use the Arclength function to parameterize curves. And now we want to discuss why we do that. And so, see, it's just what we do is we use that S of t, and then we parameterize functions using that S of t, because then some of the basically in extrinsic parts of the parameterization goes away, and then that's the parameterization that is intrinsic. It's the natural parameterization of the curve. So what do I mean by natural parameterization of the curve? Think of a smooth curve C as a road. A parameterization R of t describes how a car drives along the road. And so the car can be fast, the car can be slow, and it's just R of t is the parameterization of the travel that the car does. And then if you're trying to let's say put markers on the road, you don't just go and place a marker every minute or every 10 minutes or something like that. If you have driven on any highway, you see the markers are mile markers, right? And so what you have is, it's just the efficient way, or the intrinsic way of doing things is that you put mile markers on the road. And so you basically are recording the value of S on the road. The value that the S of t, the Arclength function, is taking. And then into the parameter that we are using there is going to be S. And so basically the mile markers themselves give you a parameterization, and then you can write the parameterization as R of S, point in the road, S miles from a fixed starting point. So instead of that many minutes, you say miles, this miles from where you start. And then there's a special property of this parameterization. We just discussed that the speed is what? The speed is ds dt for speed for parameterization. R of t is ds over dt, and it's equal to the derivative of the parameterization at time t. Now, if the parameterization is S itself, then I get ds over ds is equal to that. And ds over ds is the derivative of s with respect to s is just 1. And so the speed is going to be 1. And that's the special property of the Arclength function parameterization, or Arclength parameterization.